Welcome back, all students, and it's my pleasure to see you again. In this chapter, we are going with the design of the sewers, and as a review, I'm going to tell you to talk about the sewers. We talked about the sewer and the wastewater in general, and how it could be, what will be the components of the wastewater collection. There will be sewers, pumping station, and raising pipes. We need to have a treatment of sewage. There is a primary treatment, and there is a secondary and tertiary. Tertiary treatment means advanced treatment. Then after that, there will be the results. After the treating of the wastewater, there will be a disposal of the reuse of the treated wastewater to the river. Now, which kind of the sewage that we have? We have domestic, we have industrial, we have rainfall, and we have infiltration. And the infiltration, we say that this is in when we have a water table high in high level. So high level water table will make a kind of infiltration from the soil to the sewer itself, which is, and you may ask how we can have this one. Usually in the past, not now, we have the sewers that we have, usually it will be concrete sewers or vitrified sewer, vitrified clay sewer. Now, what we have, concrete or clay, there will be a penetration of, there will be a soil water table inside the soil itself. So when we have this kind of, there will be from the joint and from the soil itself, it make a kind of pressure. This is called infiltration. And we have such kind of infiltration if it is exist for the high water table area. And besides of that, if we have a type of the sewer materials, we say for concrete there will be, and there will be for clay, which is vitrified clay, there will be infiltration. While we don't have it for UPVC, or there will be very little, and it can be ignored. Then after that, we have the rainfall. We say that we have stormwater and we have domestic. So those two ones are very important, and the industrial waste it shouldn't be included in the separate. It shouldn't be included in the municipal wastewater and tourist collecting. It should be have a specific collection for itself. Anyway, we say that we have two types. 99.9 from the sewage is called water, liquid, and the 1% will be the rest. And we have combined sewers and the separate sewers. And what is the difference between the combined and separate? Can you tell me, Mishta, for example? Mishta, can you hear me? Okay. Now, this is the radial system. Okay. And what about this system? This is a horizontal system. We have houses in the level that we have here, and there is another houses here, and there is another house. So it will be look like a step like this. So the houses will be, all the houses will be collected within one sewer. And here is one sewer, but we have to collect between them. And this is the topographic of the Suleimania will help us to go with this one, interceptor system. And we have another system like this flat system. Now, the main components of the sewerage system is the sewer pipe itself, and the manholes, and the sewage pumping station, and the sewer raising force system, and the wastewater treatment plant. So we say that for the position, first of all, the manholes, we say that we have to drop to have, for example, if we wanna Let me just open the project. Yeah. So let's open the AutoCAD drawing. You can see here is the layout of any project that we have by turning this layer off. Yeah. So what should we do when we wanna? You will receive from the architecture this kind of maps or this kind of drawings. So what should we do? We should start putting. These are all the homes we have. We should start putting the manholes like this. So this is will be the first manhole. And by the way, this is yeah, this is will be the first one. You have to start from the higher elevation. You have the survey of the points. You can see this is at sessions 414, means 414. There is 103.83 elevation of this point. There is another point above that, 103.87. So means this point is higher than this one. This means you have, when you are starting putting a manhole, you have to start uh, uh, from the higher elevation to lower elevation. So you have to start for this one. You will have to put a manhole here. This is one manhole. And it should be like this. Within the, you have to use the streets. It will be better, especially if you are using the continuous one. And you have to put another manhole here. And you can see there will be the elevation at this manhole is how much? It's 200, 300.
103.
Yeah, I think it's something. Yeah, 103.5. 103.5 will be for this point. Now we have 102.16. So the direction of the sewer will be like this, from this manhole to that manhole. And because the distance from this manhole to that manhole is more than 100 meters, how do you know the distance from here to there is 100? You can just use the dimensions.
Don't we have the measurements? For example, 103 to...
Yeah, that's for the direction
That's the
from
elevation.
which manhole to which manhole you are going to use the direction of the flow. But when you want to see how much is the distance from this manhole,
So,
because
doctor, that is the elevation, correct? The
yeah, the red
103?
one is the elevation,
Okay, got it.
but the distance you can take it from, that take a dimension from here to there. I'm sorry, we have something wrong. Yeah. For example, if I want to take the dimensions, here's the dimension from this manhole. You have to be aware when you are using snap off. Okay, I will take this way. I'll start from here. You can see how much is the distance. It's 112 meters. Am I right? Hello?
Yes, doctor, yes.
Okay, so 112 meter, it's from the corner of this building until this corner. So we have to put a manhole here, we have to put another manhole here, and because it's more than 100 meters,
You need
usually
one in the
it
middle.
will be prefer to put another manhole in the middle of this street. So that's why we need 3 manholes, one in the beginning, one in the end, and one in the middle. That is what we needed to put it. And uh, the layout of the manholes very essential in the beginning of the design of the source. Back to what we have in every intersection we should place also manhole, and also we have at the change of the direction we say that we have to put a manhole, and we have to be allowed for a maximum distance should not be more than 100, and here's the directions, and here's the now back to how to design. What should we do when we want to design or find the diameter and the slope of the source? Usually, the calculation of the flow will be like this. We have the water consumption. This is called water consumption, which is equal to, for everybody, every capita, how much is the water consumption for every people, every capita?
150 liter per
150 liter per capita per day. This is the average, right? So we need to take 90%, 80% till 90% of this amount, and we consider that the supplied water, 10% will be used for every capital. So we will use, that will go with the drinking. So usually 25 liter to 30 liters will be used, vanished. So the rest will come with sewer. This is the rest will be used as a waste. Now that's for every capita. So what should we do? We should multiply the people that are living in that area times the water consumption times the 80% to 90% to get what? To get the flow. This is called the flow. This is called water consumption. This is the sewage, and this is the average flow. Okay. Now, as we had in the water's consumption, the peak factor, and what was the peak factor for the water consumption? The peak
1.8
factor is equal to 1.8 times
times
T
t to the power minus
minus
0.9.
1, right? And T should be in day, right? This is what we have related to water. For the wastewater, we have another peak factor method, which is equal to 18 times plus square root of the PP in 1,000. And we have 4 plus P square root of P, or P over 1 over 5. This is the maximum. It means that for example, if I wanna have, if I have a city, for example, an area, and the population living in this area was, for example, 12,000 capita. So how much it will be the Q average for those 12,000? It will be 12,000 people, and we have the water consumption for each people, each capita is 250 liters, means 0.25 meter cube per day per capita, right? Times, let's say we will take the worst condition, which is 90%. Now, this is comes Q average per day will be how much?
2,700
2,700
liter cube per day.
per day. And this is what the average flow from that area. Now, what will be the maximum Q? Q maximum, it will be a factor, peak factor,
Times Q average.
times the Q average, right? So what is the peak factor? Peak factor we have to say it's equal to 8 plus square root of P, 4 plus square root of P. Am I right?
It's 18 plus pi.
18, sorry. I'm sorry. And then it's equal to 18 plus. How much is the value of p now? It's equal to square root of
12.
12. Exactly. Plus 4 over square root of 12. Which means how much? Just let me check the formula. Yeah, it's 18. So
Sir, it is equal to 7,764.
7,000. No, this factor. Just
No, the whole.
no. I want just this factor because there is we have a reason for this one. It's 3.646 plus 18 divided by square root of 12.
Sir, I think it is equal to 2.89. 88, for example. 2.88.
Just let me check this one. Yeah, 12. It's 2.87. 88. This is a factor, and there is this p factor. You have this one or another formula, because it says that the maximum of either this or 5 over p over 1 over 6. So 5, let me check, 5 over square root, not square root, p power, p, which is p power 1 over 6, which means 5 over p is 12 power 1 over 6. And calculate this one also.
Sir, it is equal to 3.3.
Yeah, so it's equal 3.3. Now, the peak factor, it should be the maximum of these two numbers, which is equal to 3.3. Okay, then I say Q maximum is now equal 3.3 times the average Q, which is 2,700 meter cube per day. And will become equal to equal to 8,922.16 meter cube per day.
Sir, it is equal to 8,910.
Okay, 910.
Yes, doctor.
2,910 meter cube per day. Okay. Now, this is one. So what we need for the flow to have at least the minimum flow, the maximum one, and also there should be a Q minimum. The minimum should be, I say that it's equal to 20% of the Q average. As so 20%. So your design should be for Q minimum and Q maximum. Why we have Q minimum? Sorry, it's P minimum, which is peak factor, it's equal to 0.20% of this of the P or 1 over 6. P 1 over 6. Now for our case of the this is 20% of this. 20%. It's 20% times peak factor, population of 1/6 times the Q average. Now, how much is this? It's 0.2 times. How much is the population? We have 12. And 12 thousands, it means 12. You have to take as a 1,000. 1/6 times the Q average, which is 2,700 meter cube per day. So the Q minimum,
It is equal to 870.06.
817,
17,
yeah,
06,
0.6
06.
or 6 meter cube per a day. So now your system should come, so I can say that design criteria, it should be Q maximum and Q average and Q minimum. Well, Q average 2,700 meter cube per day. The Q minimum was 817.06 meter cube per day. And the peak factor 8,910 meter cube per day. Okay, now the variation in the Q means we have flow maximum. What that means, you have to have a pipe. The sewer should be, if I'm using a circular, I'm sorry for this horrible shape. If this was the cross section of this sewer, means that we have the level. This is the level of the flow, and this will be the maximum level. Also, we don't want to have the empty sewers. We want to have it, and this will be the minimum level of the flow in the sewer. And also there will be an average level. And this should be kept empty. So this is the design. Your design should be complete. At the maximum level, when we have Q maximum, when we are designing such kind of source, it means that you have the diameter. This is what we call as the diameter of the sewer. And usually we are denoted by D. So D should be the diameter of the sewer, okay? Now, there is another D, which is usually called by small d. It will be from the bottom, but it will be till the level of this sewer D. D is the depth of the flow in the sewer. So now you know what is the capital D and what is the small d. Usually why it's capital? Because it's the greatest value of the sewer diameter, which is the sewer diameter itself. The small d is the depth of the flow at any level that we have. So I will ask you, if D over capital D was 1, what that means? Can you answer this?
It means that there is a full flow in the pipe.
Flow. Yeah, it will be fully sewer flow. Am I right?
Yes, sir.
Okay. So usually the D over D will have a value which is equal or less than 1. And for the design purpose, we will keep this D over D should be less or than 0.70 75 or just 75% filled. Now we will leave the distance will be look like this. Now at each level there will be a Q, right? So we have velocity in that level. So for Q maximum, we have V maximum. We have for Q minimum, we have V minimum. Am I right? Now,
Yes, doctor.
Yes, doctor.
so the maximum velocity that is the design criteria is asking for it shouldn't be more than 1.5. I think it will be meter per second, and also the minimum velocity shouldn't be more than 0.6 meter per second as if there was in the water. Let me check this one. These are all the velocity. So these are all the velocities criteria should be, and why it's 0.6 should be created more than this one. We don't want a very slow moving of the flow because we want at least the velocity should be enough to just keep self-cleaning for the sewer itself. And also we don't want to have a more velocity, high velocity to prevent the sewer erosion. And this is what we related to the sewer velocity. And how do we have to calculate this sewer velocity? We have an equation for that, and it's called Manning formula, which I'm coming to mention it later. Okay, so for Q, we have Q maximum, Q minimum, and average. We have for velocity, we have V minimum, V maximum. So as if you are checking the design, you should follow these velocities. Okay. Another important thing for the gradient of the sewer, the slope. The slope of the sewer should be greater than 1/5, or 1 of diameter. This is the diameter itself, diameter of the sewer. For example, if you are using 250 millimeter sewer pipe, if you are using this one in your design, and there is a manhole here, and there is a manhole here. Okay, the sewer is starting from this manhole onto this manhole. So, and this will be 250 millimeters diameter, and we have the level here, and we have a level of the sewer here. So the slope, this slope, it means we have the distance between this manhole to that manhole. For example, if the sewer was 100 meters, between manhole to manhole, it will be not to be more than 100 meters. Let's keep it 100 meter. So how much will be the drop from this elevation till this elevation? It say that the drop should be more than 1/d. What does that mean? 1/d, which means 1/250, but you have to know that in millimeters. So 1/250 millimeters times the length, which is, and when I say 100, this is as a number, not as any direction. So 1/250 times 100 meter, which is
0.4.
how much?
0.4.
0.4 meter. So at least this sewer should be more lower than the starting. This is called the invert level. The invert level of this sewer, it means the bottom level of this sewer, and the bottom level of this sewer at this manhole. The bottom one, the manhole number 2, bottom sewer, and manhole number 2 should be lower than the invert level of this sewer in the beginning, in the start one. At least you should have 40 centimeters or more. This is called minimum slope. Why we need to have a slope? Because we want to guarantee the flow by gravity. We don't want to have a flow stack. The flow will be stacked in the sewer. We want to have a flow inside the sewer. So this is called the minimum slope. And you may have more than this slope. So you are, as a designer or as a checker, you have to see the level, the bottom level, or the ground, the starting and the end of this source to see how much it will be minimum drop down of this manhole. That's one. Besides of that, we have some of the manufacturers of the sewers, they will tell you what will, yeah, like this. You may have this kind of pipes when you want to buy these. This is called corrugated. This is called corrugated outside. There's this is called corrugated like this. Corrugated pipes, which is called outside corrugated pipe. The slopes is given to you, minimum slope. This is the diameter of the pipe. For example, for 100 or 4-inch pipes diameters, the minimum slope will be at least 2.25%. 2.25% means what? Means 2.25 centimeter per 1 meter. Every 1 meter, we have to have 2.2 centimeters. Or in this case, if I have 100 meter as in the previous example, so how much it will be? You just have, 20, sorry, 2.25 centimeter. So 2.25 divided by 100. This is will be the required. So yeah, for 100 meter, sorry, for 100 meter, we have to have 2.25 centimeters. This is this percentage, you can say 2.25 centimeter per 100 meters. Am I right? You just keep, if you want to just have in percentage.
That way we'll get 0.0225.
Percentage.
Yes.
Yeah. So 2.25 percentage, it means per 2.25 per 100 centimeters. Yeah, am I right? 2.25 centimeter per 100 centimeters will come with how much? With 0.025, right? Centimeter, or it will be 0.2.25 or 2.25%. Am I right?
But doctor,
Yeah, sorry. So 2.25 centimeter per 1 meter.
1 meter.
Yeah, 2.25 centimeter. This is drop, and this is length, the horizontal length for every 1 meter. And what about 100 meter? So there will be 100 times 2, 2.25, 225 centimeter drop down, which is 2.25 meter.
Yes.
So yeah, from a manhole to manhole, where the distance, the horizontal distance, which is the distance that you are taking by using the AutoCAD, because the AutoCAD is giving you the horizontal, totally horizontal one. So for 100 meters, you will have at least, you have to have 2 meter drop down. Means what? Means if the starting manhole here, this is the manhole that I am going to start with, and this is the ground level. So minimum you have for the first manhole, you have to keep 1.5 meter. This is the starting one, excavation. And then you have to use and the sewer, that's here, we say that we have 4-inch manhole. And you are keep going until you get the second manhole. The second manhole, and the distance between this manhole and that manhole is 100 meter. So what will be the depth of the second manhole, it will be the depth of the first manhole, which is 1.5 meter, plus the drop down. Here's the drop down, how much I dropped due to the slope. It was 2 meter 25 centimeters. So the result, there will be 3 meters 75 meter. This is minimum. So the minimum manhole depth will be 3 meters 75 at the second one. And guess what? What will be the third manhole excavation? That's when we have a flat area. So it may have 6 meters. So that's why we cannot keep going for the fourth one. So you have to use, this is if you have a flat area. It means that for the flat area, you may need the fourth one. It should be turned to another kind of manhole. It's called drop manhole or pumping station. Yeah, so my point was that sometimes there will be 1 over d in minimum, millimeters. This will be the minimum. The slope should be greater than this factor. This is in millimeters. You have the slope to be kept more than this one, or use the provided slopes by the manufacturer. You can see, like you say that this slope will guarantee to you. If you have a pipe flow to put it in this slope, which is 2.25%, it will be guaranteed to let the flow with a velocity 0.75 meter per second. We said that the minimum V minimum is 0.6, right? And this factory or this manufacturer is not, they believe in 0.75 as a self-cleaning velocity, not at a 0.6 meter per second. Anyway, you have to follow what is the manufacturer is asking for. And the drainage height is 20, and when we have this one, there will be minimum flow, and it will be 20%. 20% means D over D kappa will be 20%. Okay?
Doctor,
Yes.
where we use the inverted siphons.
Inverted siphons.
Yeah.
When did you hear about this siphon, inverted siphon?
Yesterday, I saw a video in Practical Engineering YouTube channel, and they were talking about the sewers. And one case they talked about it is when we have an elevated surface, for example, and we want to give a uniform slope to the pipe, and in the middle of that we have a river. So in order to
and this is
avoid those,
I said if you we have in Dukan, you can see in Dukan river, Qashqali river, we have the cities living here, and there is a river, and will be the outlet of their sewers. Okay, so it was a project, and the project is to collect all the sewers of this city, you can see, and what to do, treat that sewage. So I have a project on this one, and I give them my design. First of all, we have to collect all the sewage that we have from Dukan district here all together. Now, because we don't have any area here to use it as a wastewater treatment, and we want to have it far away from the intake, we should use another area. Here's like this one. So what should we do? We have to use to pass the collected sewer to this part, the other part of the bank of the river. So we are using a kind of pipes called inverted siphon. Inverted siphon, it will be look like this. We are using it when we have a sudden drop down of the sewer. So and there is by the way, we cannot use a very high drop. There will be this is called inverted siphon. We are using it in this kind because the bank is lower than the bed of this river will be lower than the banks. Well, and for this kind of, we are using an inverted siphon. This is the method of, or the location, very suitable location for using the inverted siphon. Now, how to design the inverted siphon and how to use it, this is another thing. This is another, you have to be, we are taking this one in hydraulic structures, and it's early for you to take this one because we have to keep a velocity. We are using a change in diameters will help us to push the water and have extra pressure on that one just to let the flow will be run away from this pipe to another pipe. This is another method, or we need let me special lecture for this one, and usually the graduate student will. But
Doctor,
this is the one, yeah.
I've heard that, like in this case, and the case of the inverted siphon, they use a smaller pipe diameter with two
Exactly.
pipes in order to make sure that there are not a lot of settlements, and so that to prevent.
Yeah, small, and usually there will be three pipes together, and usually we have to have the level of, we have to have a level of the sewer in the beginning, or should be
Same as
more.
the end.
Yeah, you have to take on, we need to have the level, the differential level between the start, and should be enough to let to have a pressure at the beginning to just push that sewage that collected here to come to this manhole. So it needs a kind of design criteria.
Thank you very much. Appreciate it.
Now, back to, we said we have, that's what I talked to you, that will be small d is the depth of flow, and this is the capital P. It will be the depth, whole diameter of this span, and this is the L, the length, and the slope minimum. Now, we say that we have, this is the minimum and maximum flow, because those two flows, which is depend on the population, and we have its maximum, its average, and its design. So Q maximum, average, and minimum. This is for population. So this is when we have a separate separate system. So in here it's called dry weather flow. Dry weather flow, it means uh, we don't have the rain. We don't include the rain in this calculation. We don't include the Q of the storm that we will have it if you have a combined system. So what about if we have a separate system? What if I have a combined system? So what we should include the Q that we will have from the rainfall. Now, what will be the Q that we have from the rainfall? This is another course. This is called Water Resources Engineer. I think you took that one. You have an area and you have the CIA infiltration and so on. As a result, you will get a Q, which is called Q storm or rainfall storm. Now, we should include that Q or add them to that, what we have it here. So adding the Q rainfall here together, then this is will be in another case. This is will be in another, which is called, this is for the dry weather flow, just the maximum and the minimum, and this is the populations and the infiltration, by the way, if found, when I say if found it, if there is infiltration. For wet weather flow, it means that we have a storm water. The storm, so the storm water, the wet weather flow, that means we have to include what we have it from the population plus the storm, the rainfall. And again, this rainfall usually will be Q rain will be equal to CIA. C, coefficient of the land, I, infiltration intensity, rainfall intensity, and A is area. And I think in water resources, you took that one. So adding them together will give you another Q, which is called Q maximum, but this time it's wet. It's due to storm, there is a wetness. Q minimum will be the same Q minimum that we have. It means that there is no rain and there is a minimum flow in this one. So here is the summary. The summary is we have to design our sewers based on the following: Q, and if I have separate system, and if I have combined system. For separate system, we have Q minimum, max, Q min, Q average, Q minimum. And without Q rain is 0. Then what will be the maximum? Will be equal to Q average times a peak factor. Peak factor, we have either maximum of two things. Either it will be P over 1/6, or I think 5 or 8. How much is to divide 5 divided 8? And we have 18 plus P and 4 plus P. And again, the P is equal to population in thousand. The minimum one is equal to Q average times 0.2 times P over 1/6. While when we have combined system, we have to include the one that we have, and this is called dry weather flow. This is called wet weather flow. Q max and Q minimum. Q maximum is the maximum of population plus Q rain, and this is will be just minimum of population. And that's it. This is all the summary that we will have. Do you have any question right now or till now?
No, Doctor, thanks.
Do you want to take a break? Because we have to, yeah, we have to just go through one examples and then
Let's just finish it.
let's just finish it. Okay. And now this was the summary and all the processes. And back to, we say that we have the velocity, the minimum velocity. Here's the usually the equation that's used to calculate the velocity, which is called Manning equation. Manning equation is the most common one that's used for calculating the velocity in the pipes. Let me give you some. We have for velocities in pipes. We have three common nowadays used equation. One's called William-Hazen equation, and the other one is called Manning equation. The William-Hazen equation, it will say that the velocity is equal to 0.355 times c times r times s, r 0.63 and s 0.54. What is the r? What is the s? And what is the c? This is called coefficient, William-Hazen coefficient. The r is called hydraulic radius, and s is called the slope, hydraulic gradient. Hydraulic radius, it is hydraulic radius definition is said that it's equal to area divided by rho. This is area divided by weighted perimeter. For example, if you have a pipe like this, if you have a pipe like this. Okay, now if we have, and by the way, the problem, what's the difference between William and Manning equation? They only used for fully flow. Used only for fully flow. Means when I say the area, if I have the diameter of this pipe is D, so how much it will be the area? Area of this circle is pi d squared over 4, right? Hello?
Yes, Doctor.
So what will be the area of this circle, of this sewer? It's pi d squared over 4.
Yes.
Now, what will be the parameter of this pipe? What is parameter? It means that, tell me about if I have this fully sewer here, it means how much is the distance will be the parameter that will be weighted due to the flow. So this is rho. If in case that we, let me say, if I have a circle like this, and if I say the sewer level was, or the flow was here, so in this case, what will be the parameter? It means that the distance that will be weighted, it will be only this distance. This is the weighted parameter. The weighted parameter, it means the connected, or the touched between the liquid and the pipe. So the distance that will the liquid or the sewer will touch the pipe, that's the liquid. In this case, because we have a fully flow, so the weighted parameter will be the circumference of this sewer, which is pi d. Am I right? So can cancel out, d will be cancelled out, so d over 4. This is the hydraulic radius for fully flow pipes, which is not exactly the same one that we have it here. And the S is the slope of the gradient. And this is when we have for fully flow, and usually we use this equation for Manning, William Hazen for the design of the water. And usually you can say the Q is equal to VPA, and you will find the relation, and the S, as I told you, is the head loss divided by the length of the pipe. How much it will be the length? Let me say this is the pipe here. Will be the pipe, the length of the pipe, and the level that we have it here, the level of water. So the level of will be the level. So this is the HL, so the HL divided by L, HL over L, which will equal to 1 over S of the slope. That's the slope used. So it's not a slope of the pipe, it's hydraulic slope. But because there will be very little difference between the slope of the ground and the slope of the pipe, we use it as a slope of the pipe itself. Actually, it's the hydraulic slope. It's not the slope of the pipe, but the slope of the hydraulic one, it will be very little, and they will near together. That's why in the design we are using it as a slope of the pipe. This is what we have it for the William equation. That will not be used for the water, the sewer. What we have it for the sewer, the velocity, it will be equal to 1 over n r to 2/3 s 1 over 2. It just will be, it will be close to this one, but here is 0.63, here is it will be 0.67, and there is 0.54, this is 0.5, and there is a C 0.3553, and C, which is the William Hazen. We said the S is between 100 to 150, and here's Manning. The Manning coefficient. The Manning coefficient, usually for a certain pipes, we have its n. Remember that. Let me just go back to the lectures. You can see in the table that we have for the minimum slopes, Yeah, look at this Sn. The Manning coefficient for such kind of pipe it will be given to you. And by the way, for the plastic PVC, the N is 0.01, and for concrete pipes, we will have N equal 0.01013. We need to know it's a roughness of the pipe. It will depend. For every kind of the sewer materials, we have its own N. So we have, will depend. For concrete, will be equal to 0.013. That's the N. And the N will be 4.01 if I have PVC, and so. Now, when we have the R, it will be in meter. Then the velocity will be in meter per second because this is unitless. And N, it will be a unitless coefficient. Will be the Manning. And it will be used for finding, it will be used for open and closed pipes and fully or partially filled. Now, this is what we'll use it for our design. Now, if I have, this is an I have here, and was the diameter of the pipe, and this is the depth of flow. So usually we have small d over capital D. For such a small over capital D, if I have d over, if there was 100%, you can calculate the velocity, the Q, and this is called Q full. So Q full, when we have fully flow, and when we have d over capital D is equal to 100%. And if I have d over D, for example, 5%, if d over D was 50%, then the Q will be Q half. And it will be half a flow. And for any value of d over D, there will be a ratio between Q over Q full. And what will be that ratio? We can use it because it will be difficult. It will be difficult to find the flow when we have here. There is a relation between. So what you need just to find the Q full and multiply that Q by a factor to get the Q at this depth. Okay. The relation we have curve for this one is called partial flow curve, and here's the partial flow curve. Yeah, so this is d over d. When we have d over d equal to 1, the Q, the element, this curve is for discharge. Discharge, I mean by Q over Q full. So when we have 1%, we have to go with the 1 and on the curve, and you will get back, sorry for that. You have to use for this one. You can see at d over d, the Q that we will have is equal, you have to go with the curve of the Q, you can get a number. But this number, it means this will be equal to Q over Q full. Means the Q over Q full is equal to 1. It means the Q at this point is equal to Q full. But in case that I have d over d equal to 0.77, 70%, what will be the Q at this one? You just have to calculate the Q full and then multiply this Q full by a factor. Where is the factor? This is the factor. You have to go with the 0.7 and intersect with the curve of this one and go back to here. You can see here's 0.9. So you just multiply the Q full that we have by 0.9 to get the Q. So it needs a kind of using the graphs. This is what called as a partial, or this chart It's very important in the design of the sewers. It will give you the related Q to the related depth of flow. That's what we have. And if you can see, there is another curve, which is the velocity. And also by having d over d at a certain point, we can get the velocity. The velocity, the ratio for v over v full. Why all the denominators are for full flow? Because for full flow it's very easy to calculate the Q at full V full, because Q at full flow is equal to area times the velocity at V full. And the area we can have it is pi d squared over 4, and the V we can have it by 1 over n r power 2 over 3 s 1 over 2. What is the r? It's r for circular diameter is d over 4. And it will be very easy to find this one also. So Q full is very easy, but the Q at when you have a differential flow, it will be a kind of difficulty. So you have to use this chart. Firstly, you have to find the full Q full and then multiply that one by but this number to get the real. This is called real flow at that depth. I think it's very late. Now you have the whole ideas. I will record a video for you and at a time we will in the Sunday we will have a quiz on the water, not on the sewer, chapter 5 only. And also I will record a video for you to how use the graphs, and I will solve the rest of the examples that we have in the chapter through that video.